One interesting feature of this particular reaction, the electrophilic addition to this conjugated alkene, is that the product ratio of this reaction can be altered drastically with a change in temperature. Okay, we saw before how there are two products. There's the 1,2, right, where the H is on the end and the bromine's added just next to it, and the 1,4, where the H is on the end and the bromine is 4 carbons away from it. At 0 degrees, we favor the 1,2 addition. At 40 degrees, we favor the 1,4 addition. This phenomena is common, actually, for reactions that produce a mixture of products. Okay? Some reasonable mixture of products. If you cool it way down, you can get one. If you heat it way up, you can get the other. The reason for this is that there are two different methods of determining which product is favored, and we actually already know about them. We've studied kinetics and thermodynamics for quite a bit, ever since second semester chemistry and earlier on in first semester. For reactions that are irreversible, reactions that only go in the forward direction, the product that is formed fastest is the one that is favored, right? So that's called kinetic control, which if there's a normal mixture of products, if we can have an irreversible reaction, whichever one is formed fastest is just the one that we'll be favoring, and that's it. A reversible reaction, one that can form the product but then back to the reactant and back and forth and so on, that depends on which product is the most stable. It has no bearing on which is the fastest because it's a reversible reaction. We can go back and forth and we have access to all possible reactants and products. Whatever is the most stable then will be the one that is the most populated in this case. So what we can end up doing, we end up with a reaction energy diagram that looks like this, starting with a common reactant, being able to form two possible products. The diagram the book used is A becoming either B or C. Right? Under kinetic control, if, say, we only have enough activation energy to just get over this barrier and not the higher barrier, then this faster reaction here is the one that'll be formed, regardless of product stability. Okay? Even though C is more stable, we can't get there because we don't have enough activation energy to get over that barrier. Whereas, on the other hand, if we have plenty of activation energy to get over anything, right? If we have a reversible reaction, if I could go down here, but just as easily come back here, and get down here and just as easily come back here, if we're able to do all of these things, then the reaction will settle into whatever is the most stable, whatever is the lowest in energy. We can influence which of these paths the reaction will take by influencing whatever it is that provides the molecules with the activation energy. Okay? If there's barely enough activation energy, then this is the major product we'll get. If there's plenty of activation energy, everything will happen, and then the more stable product we'll get. So we, of course, can control how much activation energy we provide the reaction by heating or cooling it, right? The temperature of a reaction is directly related to the amount of kinetic energy that these molecules have. And remember, only those molecules with enough kinetic energy to traverse this activation energy barrier will be able to react. So if I cool the reaction, then very few molecules will be able to get any further over than this point right here. Okay? If there's only just enough to get over this point, then very few will be able to make it over this point, and they'll land down here. It'll be irreversible because if they can just get over this barrier, then they won't be able to get up over this barrier, right? So kinetic control can happen when we cool a reaction. Thermodynamic control is where we provide plenty of energy. If we heat a reaction, it can get over all of these barriers. The barriers are no longer the issue. Okay? We'll have access to all of these states, to A, to B, to C, and we'll have a product ratio consistent with those differences in energy, where C, the lowest in energy one, will be the one that's favored. So if we look at our products here, an adduct is just a name we give for a product of a reaction. So the 1,2 product, sometimes it's just called the 1,2 adduct, right? So if at 0 degrees, when we cool it, we get the 1,2, that must be the kinetic product, the one that forms faster. If when we heat it up to 40, we get this 1,4 adduct, that must be the thermodynamic product, the one that is more stable. All right, so the trick in this is figuring out why it is that the 1,2 product forms faster and why it is that possibly the 1,4 product is more stable. This is a very useful scheme for us to have, and it'll pop up a couple more times this semester. If we can figure out a reaction that happens faster in one case, but a more stable product can be produced more slowly than it, we can have access to either of those products that we can choose just by controlling the temperature. So let's figure it out with this one. Remember, the key intermediate for this is that resonance stabilized allylic carbocation, right, that exists between these 3 carbons. Right here, I'll just circle them in the intermediate. Okay? And depending on which of those carbons the bromine attacks, that's what determines which of these 2 products we get, 1,2 addition or 1,4 addition. Well, let's take a look at the carbocation, the resonance structure for 1,2 addition. Here, let's just redraw it. There's one resonance structure. Here's the other resonance structure. Both of these combine, right, to make this one overall picture, and the electrostatic potential map shows us that the plus charge is distributed between carbons 1 and 3, but the secondary carbon, oops, I drew the same one here, didn't I? Let's draw the other one. There we go. There's a secondary and a primary carbon that shares the plus charge, right? Here's the secondary one, here's the primary one. Normally, secondary carbocations are more stable because they have more carbons around them that can donate in a little more electron density to them. So what happens, this picture right here actually shows us that there is more positive character, more positive charge on this secondary carbon than there is on the first, right? Because that secondary carbon can better stabilize that positive charge. So, just because of that, the nucleophile will more readily attack that secondary carbocation. And just the attraction of opposite charges. If this has a stronger positive charge to it, it will more strongly attract the nucleophile to it. So if we cool it down, and only the very fastest thing, only the thing that, based on this intermediate right here, is the easiest to happen, right, then we're under kinetic control, and we end up with the bromine attached to that secondary carbon. That will end up giving us 1,2 addition, which is kinetic control in this case. Now, the product of 1,4 addition, here, I'll draw it. Here, I can draw this one just as easily. That's the product of 1,2 addition. But if we're under kinetic control, the product doesn't really matter. It's the transition state. It's whichever transition state is lowest in energy, right? Whichever of those barriers is easiest to get over. So the product of 1,4 addition actually is more stable because the double bond is more substituted, right? This is a mono-substituted double bond. All right, only has one alkyl group. Over here, this is a di-substituted double bond. Di-substituted double bonds are more stable than mono-substituted double bonds. We learned that in the alkenes chapter earlier on. So if we have access to this product and the reactants, and everything is all reversible and going back and forth, we'll settle in to having the most stable product overall. So this is a graphical representation of the reaction we just talked about, right? We end up, the first step is the same because we form one carbocation with two resonance structures, okay? Only one resonance structure is shown here, but you can very easily draw the other one. Yeah, let's just do that. There we go. So the secondary and the primary, okay? Both of those exist right here on their own. Here they're being attacked by the bromine. On this lower one, the bromine, so here let's make that black. This lower one, the bromine is attacking the secondary. On this higher one, let's do red, the bromine is attacking the primary. So remember, it's easier for the bromine to attack the secondary one because that's a stronger positive charge. Okay? That'll be a lower energy transition state than this one, which is a higher energy transition state. So this happens faster. If that happens faster, we end up with the 1,2 product, and that's it. If we have energy for all these things to happen, we can do the lower energy transition state, the higher energy transition state, the lower energy product, the higher energy product. All of these are interconverting. We end up settling on the lowest energy product because it's a di-substituted double bond as opposed to a mono-substituted double bond. So be able to understand the factors that influence kinetic and thermodynamic control. Understand that kinetic control involves the stability of a transition state, for instance, while thermodynamic control involves the stability of a product.